In this lecture, we will conclude our discussion on the Morse-Mail complex by discussing some applications. I'll begin again by focusing on the importance of simplification and the computation of a hierarchy on the Morse-Mail complex and how this impacts the different applications. After this, I'm going to talk about how the Morse-Mail complex has played an important role in the analysis and visualization of scientific data by looking at two applications that use the two-dimensional Morse-Mail complex and two applications that use the three-dimensional Morse-Mail complex. While talking about these applications, you will notice that they come from a diverse set of disciplines, application domains. I am going to give the references to the corresponding papers and briefly mention the problem that is addressed. The details are in the paper and are meant, and these references are meant as optional reading. I will focus on how the Morse-Mail complex played a key role in the application. Of course, the details are too much to cover within the lecture and within this course. Let's begin by talking about again the cancellation of a pair of critical points. We saw in the previous lecture how we can cancel a pair of critical points whose Morse indices differ by 1. So for example, here cancel a pair UV, a maximum saddle pair whose Morse indices differ by 1, in order to give a smoother function as shown on the right. So as you can see, the cancellation allows one to go from a Morse function with k critical points to a Morse function with k minus 2 critical points. And repeated application of such cancellation operations will lead us to simpler and smoother functions. So this sequence of cancellations corresponds to a sequence of smoother functions, and hence leads us to a hierarchy of functions. So one can choose any function in the hierarchy based on the parameter. Now this parameter, for example, could be the measure of how important this critical point pair is. For example, here the critical point pair UV, the importance of such a pair UV could be measured based on the height of U over V, or based on the volume under the mountain defined by U, and so on. So these notions of importance can be used to identify which critical point pair to cancel, and hence resulting in the hierarchy. Let's begin by talking about some of the applications. The first application is to 2D and follows from the paper that introduced one of the early algorithms to compute Morse-Mail complex. This looks at how to visualize terrains using the Morse-Mail complex. What you see on the top is a terrain of the Puget Sound data, that is of the coast of the US. And on the bottom you see the Morse-Mail complex computed for the height function. And the animation shows the simplified function, and now this is the video is playing back to show the different features that were removed, the different critical point pairs that were removed, which are getting inserted again. Let's see how this simplified Morse-Mail complex helps a fly-through. During a fly-through, you would like to see high resolution within the camera's field of view and low resolution elsewhere. So this allows for efficient rendering using optimal use of the graphics hardware. Now what you see now is essentially how the data is processed. So the frustum that you see on the top corresponds to the camera, and you notice on the bottom that the Morse-Mel complex is represented at high resolution inside the camera frustum and at very low resolution outside, thus allowing for a small enough representation of the data while preserving all the necessary details. The Morse-Mel complex has also been used to partition or segment generic surfaces, such as those that come from the study of biomolecules. In the study of biomolecules, it's important to be able to segment the surface into peaks that are mountains and valleys. Now we already saw that the descending manifolds capture the various mountains. However, we also saw that these mountains go all the way up to the local minima. So for example, the maximum here, M1, has a descending manifold that goes up all the way to the various minima that you see bounded by the blue curve. What we may refer to as the mountain is shown by the dashed line, and we may not always want to go all the way to the minimum. Using the Morse-Mel complex, one can actually resegment or repartition the domain so that you get all the peaks, for example, shown using these dashed edges that correspond to M1, and similarly the dashed edges that correspond to the max M2. So these are the two peaks, and the complementary regions corresponding to each minimum. For example, what is shown here, right, give you a good representation of the valleys corresponding to such minima. So this peak valley segmentation can be derived from the Morse-Mel complex and has good applications in the study of molecular surfaces. A molecular surface is computationally derived from electron density data, and here is a rendering of one such molecular surface, and various scalar functions could be defined on top of such a surface. In this case, the scalar function that's plotted here using grayscale is simply the curvature at that particular point. Now this curvature could be used to identify protrusions and valleys. So in this particular case, the curvature function is used to compute the Morse-Mel complex, and what you see here is the segmentation of the surface into peaks and the valleys that I talked about in the previous slide. So all the peaks are shown in darker shades and the valleys are shown in lighter shade. So you can already see that this peaks and valleys here seem over segmented. There are some peaks which contain which are segmented into multiple pieces. A simplification of the Morse-Mel complex allows us to obtain the right level of segmentation, as we see on the right here. So what we see here on the right, for example, is one such segment, the green segment, which is able to capture a nice depression on the surface of the molecule. So this corresponds to a so-called active site, that could be the location where another molecule or a so-called ligand could come and bind with this particular protein molecule or a biomolecule. So the Morse-Mail complex helps identify such depressions and correspondingly protrusions on the surface of the molecule. And this segmentation is the precursor to the computational modeling of how proteins interact with other proteins and other small molecules. The surfaces that we study need not be molecular surfaces. They could be surfaces that come from scans, laser scans, such as from Kinect devices. So representing these surfaces is an important problem that is studied in computer graphics. The Morse-Mail complex allows us to come up with good quad mesh representations. We all know already that the Morse-Mail complex is a partition into quads. So here a special function based on the eigenfunctions of the so-called Laplace-Beltrami operator is used to come up with a quad segmentation of the surface. This quad segmentation is next tightened to give us a good base mesh, which is further refined to resulting in a beautiful quad mesh representation of the surface. Such a quad mesh has several good numerical properties. For example, it helps when you run finite element methods and so on. So here is an application of the Morse-Mail complex to mesh generation. Moving on to the applications to 3D scientific data. Here is an application in cosmology, specifically in the study of the large-scale structure of the universe. In the universe, there is matter, and the matter exists at different density regimes. The high density regions, or so-called clusters, are home to several galaxies, including our own Milky Way. So these clusters are connected via high density highways. These highways are called filaments. Computing these clusters and the filaments that connect them is an important problem, important computational problem within the field of cosmology. It helps the cosmologists test their various hypotheses. So this is essentially a data analysis problem. Once the filaments are computed, they also need to be visualized. So the features here of interest are the clusters, which are often represented as local maxima of a density field, and the arcs that connect two different maxima, which are the filaments. So both the clusters and the filaments appear at different ranges of scalar field or the density field. So there is no one well-defined range that is able to capture these filaments. This makes it a hard problem to extract the filaments and visualize them. So often one needs a lot of visual interaction in order to be able to identify these filaments and explore them. So here comes the use of the Morse-Mail complex, specifically a hierarchy of the Morse-Mail complex, where we begin with the Morse-Mail complex MSC sub 0 and apply a sequence of cancellations resulting in coarser and coarser representations, in this case going up to MSC sub 6. The query here is such that the cosmologist is able to capture the various filaments of interest. So the cosmologists often specify some density regimes that they are interested in. So for example, if they specify that their maxima should lie within the density regime M sub B to M sub E, one could extract all the clusters whose maxima fall within this density interval and extract all the arcs that connect such maxima. So here the maxima are shown in red, and the connections are shown using the arcs. Now we know that the arcs go through saddles. So in this case, these are called two saddles, that's shown in yellow. Now the arcs are not as simple as what is shown here. So this requires a query over the hierarchy, and the reason we need a query over the hierarchy is that the arc that connects two different maxima, two different maximums, such as the one the two red maxima shown here. So these arcs could need not be straight. They could contain various small features, so they could contain a lot of noise. The question is, how do you remove this noise? Well, one could apply a simple cancellation. However, the cancellation threshold could very well, so for example here the cancellation threshold is T, but if in the original case the difference between the maximum and the saddle is already just T, then you may end up not reporting such a highway between the two maxima, right? So it's important to not just apply the cancellation using a single parameter T, but to do this query across the hierarchy, as in you perform the simplification. For example, the first or second simplification may remove the smaller pairs, and then you try to extract the filaments between two maxima and so on. So this is again a variant of the cancellation, and that leads to an important application, namely to the study of filaments. So this particular query across the hierarchy turned out to be quite useful in an initial study on simulation data, where we know exactly what the results are. We could show this particular paper showed that the Morse-Male complex based filaments could identify all the known filaments exactly. So here is a particular so the so-called least evolved stage of the universe, where not all the filaments are very clearly visible, and followed by a so-called mid-evolved stage of this simulation and a fully evolved stage. So these are the different stages of in the evolution of the universe. Now, in all cases, the method that is based on density regimes and simplification and querying in the hierarchy is able to extract the filaments. The filaments, as you can see on the top, would be all these high density highways between the clusters which show up as these hotspots. So on the pictures in the bottom, the red are the filaments that are computed using the Morse-Male complex. So especially in the most evolved stage, we get exactly all the filaments So this clearly shows the benefit of this approach. Now we next show how this method works for more sophisticated simulations. So here is the application of this method to a so-called Lambda CDM.
We demonstrate our topology-based visual exploration framework for cosmic filaments.
Are gigantic
Cosmic filaments are gigantic tentacle-like structures comprising of billions of galaxies. They serve as a mass transport mechanism between dense collections of galaxies known as clusters.
Where the density of
Regions of
galaxies
space
is much
where the
lower
density of galaxies is much lower is referred to as cosmic voids.
in cluster-like regions
Filaments exist
and
in
void-like
cluster-like
regions.
regions and
They
void-like
also connect
regions.
cluster-like regions
They also
across
connect
void-like
cluster-like
regions.
regions
We
across
propose the
void-like
use of a
regions.
density
We propose
range-based
the
query
use of a
method
density
to
range-based
interactively
query
explore
method
different
to
kinds of
interactively
interesting
explore
cosmic
different
filaments.
kinds of
The
interesting
query
cosmic
is efficiently
filaments.
translated
The query
to
is efficiently
extract
translated
filaments
to
from a
extract
topological
relevant
data structure
filaments
called
from a
the
topological
hierarchical
data
Morse-Mill
structure
complex.
called the hierarchical
Here,
Morse-Mill
query
complex.
was adjusted for
Here,
filaments within
query was
high-density
adjusted for
cluster-like
filaments
regions.
within high-density
The
cluster-like
extracted
regions.
filaments are visualized
The
by the
extracted
orange linear
filaments are
elements.
visualized by the orange linear elements.
Filaments within voids form interesting
Filaments within
objects of
voids
study which
form
are not
interesting
easily
objects of
extractable
study
using
which are
earlier
not
methods.
easily extractable using
Here
earlier
we extract
methods.
filaments within void-like
Here
regions.
we extract filaments within void-like regions.
The queries demonstrated in this video
The queries
execute in real
demonstrated
time.
in this video execute in real time.
Thank you for your attention.
Thank you for your attention.
So what is important to note here is that the Morse-Mill complex allowed for the filaments to be extracted even in the low density regimes, which is where which are the void regions. So this was not possible using other techniques, which seem to require an expert's input on which density regimes to study. So hence this use of topology allows you to follow a data-driven approach to identify the features of interest. The final application is to in material science to the study of pores in various foams. So foams such as foams are like sponge-like materials. Foams such as aerogel are used to line spacecrafts. They are able to absorb the impact from asteroids and small meteorites. So these aerogels are mostly pores. So for example, this has 25% material. And so the study of the pores and the networks that the pores form is quite important to understand the cushioning property of the foam. So for example, we want to know answers to questions such as what is the filament structure of the pore, the length, the number of cycles it forms, how many cuts are needed to disconnect the pores, and so on. So these studies also allow for further experiments to be conducted on the structure. We used, so this particular paper used the hierarchical Morse-Mill complex to study the pore structure. So specifically what it did was to take the pore structure and compute a function that captures the distance from the surface. So the high values corresponded to the core of this pore, and the saddles corresponded to the passes between these maxima. Now what you see here is the pore network as it is. So you can see that there is a lot of noise. So it's important to be to first simplify and construct a hierarchical Morse-Mill complex in order to compute the pore structure or the pore network. One way to do the simplification is to, like I said, apply the cancellation operation. but which pairs of saddle maximum will you cancel, right? It's important to understand the entire collection of saddle maxima before you decide whom to cancel. So here is a histogram, which on the x-axis you see the two saddles function value, on the y-axis you see the maximum function value, and this is a histogram where the color indicates the frequency. So what this means is that if you have if you have a point that is close to the diagonal, which is your x equal to y line, then this means that you have a saddle maximum pair which have very similar function values. So this is a small mountain, maybe insignificant. So essentially you want to somehow retain those points that are away from the diagonal. Away from the diagonal means that the saddle is potentially small and the maximum is much higher than the value at the saddle. However, this is not sufficient. You may need to also know how many pairs there are at that particular point. So you need essentially a good way to choose a collection of these pairs to retain and to cancel away the rest. So this is where the analysis comes in. So analyzing this figure, this histogram, one can design a visualization tool, as was done in this paper, to allow the user to choose a particular box of saddle maximum pairs, and when you retain these pairs, what you essentially capture is the core of the pore network. So here, for example, we get the 372 different cycles in the pore network, as shown in yellow in the figure on the left. So this is an important problem to solve, identifying an appropriate threshold and an appropriate collection of saddle maximum pairs to retain and whom to cancel away. Right? This is a hard problem, and there are many solutions reported within the various application papers. Of course, the study does not stop here. This is not a static foam. The foam does change when a meteorite or a small object creates an impact. So how do you study the impact? One way is to capture how the pore network is displaced when a foreign object comes and impacts or hits this foam. So on the left you see the before, and on the right you see the after picture. You can clearly see that there is a crater that is formed due to the impact of this meteorite. And in order to be able to quantify the effect of this impact, one can compute the pore network before and after, which is shown in green and yellow in the figure in the middle, and you can identify where the displacement happens. So the displacements are shown in using these violet and purple lines. So you notice that there is absolutely no displacement initially, at least in the towards the right, whereas there is a significant amount of displacement towards the left, and you can also quantify this displacement and use that to understand how well the foam is able to cushion the impact of foreign objects. So that was the final application of the Morse-Mail complex. So you would notice that all these applications used either the partition of the domain or they used substructures of the Morse-Mail complex in order to capture some interesting features of the data. And the simplification method played an important role in all these applications.